engine running.
Absolute genius.
Get this.
Welcome.
This is the show where we bring you
Science.
What that essentially means is
discoveries,
advances,
questions,
Research.
technology.
Unbelievable.
Without further ado,
this is The Naked Scientists.
Hello and welcome to The Naked Scientist, the show where we bring you the latest breakthroughs in science, technology and medicine. I'm Julia Ravey.
And I'm James Titko. This week,
you would have to carry on walking until you go all the way around the Earth, and then carry on once you've returned back to the same point, and then go all the way around the Earth down to Australia, and then at that point, that's the nearest star to us.
we are walking in space where we will explore the planets on our own solar system, learn the realities of living on Mars, and jump on the James Webb hype to get a better grip on what those beautiful images are really showing us.
The Naked Scientists podcast is powered by ukfast.co.uk.
Now, if you were offered the chance to go up into space, would you want to go? A trip to Mars may sound like a big adventure, but in reality, the journey to one of our nearest planets would take an estimated 7 months. And if you're wanting to move beyond Mars to Jupiter, you are talking years of commuting. The scale of space is difficult to wrap our heads round. There are zeros upon zeros when talking about distances between our neighbouring planets. Never mind those in further reaches of the Milky Way.
Well, this week we're going to be seeing the full scale of our solar system by getting up close and personal with the planets that inhabit it.
I don't know how up and close and personal you can get with any planet other than Earth, Julia. As I just mentioned, they're a bit far away.
What if I told you that you could walk through our planets at least 5 times faster than the speed of light?
I think I'd have a hard time believing you.
Well, you're about to eat your words.
I'm walking through space.
Well, not really. I'm on Midsummer Common in Cambridge. But there is a spacewalk down here, and I can see right in front of me a ginormous sun. And I'm going to meet Matt Bothwell there, who will be guiding me through a tour of our planet.
It's the scale of 590 million to 1. So the sun we're looking at here in front of us is about a bit less than 2.5 meters in diameter. So yeah, 590 million times smaller than the real thing. But the nice thing about this whole sculpture trail is that the entire solar system is to scale. Even when you see pictures of the solar system, it's never to scale. It's impossible to get the real scale of the solar system into one picture. The only way to do it is like this, to lay the solar system out over about 10 kilometers so you can see how much space there really is.
Shall we spacewalk?
Yeah, let's spacewalk.
Oh, yeah.
We can start off, if you want, by walking at the speed of light.
Relative to this?
Well, yes, relative to this. I'm not that fast a runner. So we are exploring a 590 million to 1 solar system, and so if we scale the speed of light down by 590 million, then you can walk at the speed of light on this scale.
Oh!
And it's about this fast.
Bit of a shuffle.
It's a little bit less than 2 kilometers an hour. I think it's about a toddler's walking pace.
So if I ran along here, and I mean, I am not fast, I'm slow, I would be running much faster than the speed of light.
You would be superluminal.
Right. Well, I'm going to take that, and I'm going to do my run along here at some point and tell everyone I was running faster than the speed of light.
You could probably do 10 times faster than the speed of light easily, couldn't you?
Matt, don't flatter me. Here we are. I'll take it.
It would take us 8 minutes to do this short walk out to the Earth if we were going at the speed of light. Wow. So cosmically, the speed of light is sort of a crawl.
Yeah, a cosmic crawl. I like that. I feel like that's what I should call this walk.
Okay, we're approaching Mercury now. Do you want to describe what you're seeing?
It's a nice big purple sculpture with Mercury on the top, and it's pointing down to what looks like a bead the size of a generous garden pea.
It's sort of reddy orange, a suspect garden pea maybe. But yeah, I think it's about 5 or 6 millimeters across. It's really extraordinary when you think of how enormous the sun is, and then you see this tiny thing that could fit on your fingertip. This is how big Mercury actually is.
It's an actual chickpea?
It is a chickpea.
What's your favourite fact about Mercury?
It has the highest temperature difference in the solar system. So because there's very little atmosphere, the temperature of the sun doesn't get conducted around the planet very well. And so even though the side of Mercury facing the sun gets cooked to like hundreds and hundreds of degrees, the dark side of Mercury is freezing. It's like minus 200.
tale of two planets.
Yeah, absolutely. Actually, can I give you two facts?
Oh,
My second
come on.
favourite fact about Mercury. So Mercury is very, very iron-rich and dense. And Mercury really resembles Earth's core quite a lot. So if you think about Earth, Earth has this iron-rich core and then it's surrounded by the liquid rock mantle and the crust. Mercury really is just a big ball of iron. So one theory is that Mercury is the core of a planet that used to be much larger and maybe was involved in some sort of cosmic car crash that smashed off all the mantle and the crust and just left behind the planet's core. So it might be the leftover centre of a dead planet. Okay, so one fact about this scale solar system which I really enjoy, which is how far it would take to reach Proxima Centauri, the nearest star to Earth. So laid out on this same scale, you'd have to walk all the way around the Earth 1.5 times, and then you'd be at the nearest star.
So if I was stood here in this scale, it wouldn't be like, oh, I could walk to London and find a star.
No, on this exact scale, 8 kilometres up to Water Beach, you would have to carry on walking until you go all the way around the Earth, and then carry on once you've returned back to the same point, and then go all the way around the Earth down to Australia, and then at that point, that's the nearest star to us.
That is ridiculous.
Exactly, yeah. It feels like a long walk to Pluto, but then this is the dense part of the universe where we live, right? This is our nice, hot, dense, bright cosmic backyard. Once you've left Pluto, you would have months and months and months of walking through nothingness to reach a star.
Wow, space is big.
Right, I've heard this feeling called cosmic vertigo, this idea of almost intense, overwhelming dizziness you get when comprehending the scale of the universe. I think astronomers like that feeling.
I think they like it. That's like adrenaline for them. For me, I feel a bit Cossack.
Yeah, maybe we're kind of cosmic roller coaster junkies or something. We just like it.
Keep riding that roller coaster, keep riding it. Matt Bothwell there at the Our Place in Space project along the River Cam in Cambridge. See James, spacewalk in our backyard.
Right, got it now. The project sounds pretty amazing. I'll never look at a garden pea the same way again. With us now to tell us about this incredible collaboration between art and science is Stephen Smart, astronomer at Queen's University Belfast, who was key to making it all happen. So Stephen, what was your role in the Our Place in Space project?
It was an interesting get together originally with the artist Oliver Jeffers. It was his idea to create a scale model of the solar system. And so my job was to make it scientifically accurate and also to try and create a scale that we can relate to. So I think we have done it, and that you can walk it. You can walk to Pluto. It's a long way, but it puts the size of the planets in terms of their distances into perspective, and then puts into perspective the size of our solar system within the galaxy and the broader universe. I think the interesting idea from Oliver was not just to make it a scientific story, but to put humanity at the center of this. And that's the idea of the big Earth at the start, and then to walk the solar system and to see in reality how small Earth is.
We heard from Matt a bit earlier that, mind-blowingly, the nearest star on the scale of the Our Place in Space walk would be about 1.5 laps of the Earth away. This is your area of expertise, isn't it? Those nearest stars. Can you tell us a bit about your research?
I study stars mostly in other galaxies and stars that explode in other galaxies. So the nearest star to us, or in our backyard, is Proxima Centauri. And as Matt said, that's 1.5 laps around the Earth. So the size of our galaxy, which contains 100 billion stars, on this scale would be about the true distance between the center of the sun in Cambridge and Jupiter and Saturn in the real solar system. That's about the size of our galaxy, and that's full of 100 billion stars. Now, what I study are supernovae, the deaths of stars. They're quite rare, and so we look at millions of galaxies every night to find these supernovae, and the distances to those on this scale are about, well, at least 1,000 times the distance between the sun in Cambridge and the distance to Jupiter or Saturn. They are quite immense distances we deal with.
Absolutely. You mentioned the death there of supernovae. That's quite dramatic terminology. What actually happens when a star dies?
So all stars greater than about 8 to 10 times the mass of the sun will end their lives when the fuel runs out in the core. They survive by creating thermal pressure in the core through nuclear reactions, and they're trying to collapse under gravity. And for most of their life, those two forces exactly balance. So the force that you get from the thermal pressure and the force from gravity exactly balance, and that's why stars are spherical. But at the end of their lives, when they've burnt through the nuclear fuel in the core, they can't support themselves. So the core collapses, and that releases a huge amount of energy and destroys the star. And these supernovae can be as bright as single galaxies. And they last for about a few weeks to a few months. And that's what we search for on a nightly basis.
What about on a day-to-day basis? What are you looking for?
We partner with several telescope surveys around the world. The ones we work with at the minute are mostly in Hawaii. The nice thing about that is the time difference. So when Hawaii's observing 10 to 11 hours behind us, then it's our daytime and we can sift through the data while the telescopes are surveying the sky in Hawaii. And there's some specialized telescopes over there that survey the whole sky every night. There are 2 telescopes in Hawaii, 1 in Chile and 1 in South Africa, and they're the same type of design, and they're designed to survey the whole sky on a daily basis. Probably the first time in history we've been able to do that, to get to the sensitivity that we can achieve with these survey telescopes. And we basically look for everything that changes or moves in the night sky.
So all stars eventually meet their demise. What about our star, the sun? What's in store for that one in its lifetime?
Yeah, so that one will not create a supernova. A supernova is produced by a star which is at least 8 times the mass of the sun. So what happens with a star like the sun, these low mass stars, is that, again, their core will run out of fuel. So the hydrogen will burn to helium. The helium will burn to carbon and oxygen. And at that stage, it will not be hot enough for the carbon and oxygen to burn any further. And what happens in these stars, and we see it across the galaxy, is that they become what we call red giants, and the atmosphere swells up. So what will happen is that if you think of the sun on Midsummer Common, instead of a 2-meter sun, the sun's radius will expand by about a factor of 100. And left over in its core will actually be something about the size of the Earth, made of carbon and oxygen, and that's what we call a white dwarf. And the atmosphere, which is very extended, will then just float away and will be heated by the radiation from the white dwarf. It'll form a planetary nebula. So effectively, the sun will just swell up and eventually the outer layers will just puff away and we'll be left with a very hot white dwarf, the size of the Earth at the position of the sun. The timescales that we see and that we infer are very long. So although it's worrying that the Earth will end up within the atmosphere, a very tenuous, low-density atmosphere of the sun, and potentially be vaporized, this won't happen for another 4.5 billion years. So the sun is about halfway through its lifetime, and the Earth is about 4.5 billion years old. This will last for another 4 billion years or so until the sun becomes a red giant. Difficulty, of course, is that we can't watch this happening on a human timescale, and we have to infer the timescales through looking at stars at different stages in their lives and then applying sophisticated computer models. And that's mostly what astronomy is about, applying the physics that we know and understand on Earth through sophisticated models to the observations that we take.
Thank you for giving us an insight into your work and science communication project. That was Stephen Smart.
James, are you ready to jump back into the spacewalk?
Ready as ever.
We're approaching Venus.
Yes, we've reached Venus. It's another trek away from Mercury. We've upgraded from chickpea to grape. This thing is maybe a centimetre across. So one interesting fact about these planets, because this entire solar system is to scale, when you stand at the distance of the planets and look back towards the sun is the same size, physical, angular size, as it would actually look on that planet. When you look at the sun from Venus, that's how big the sun would be in the Venus sky.
Wow.
So it's, about twice as big as it appears from Earth.
Yeah, and I was going to say, it's really hot and sunny here today, so when we get to Earth on our next little bit of the trek, we'll have to have a look and give it a bit of a comparison.
Yeah, exactly. Well, without looking directly at the sun, of course.
I have got my sunglasses on, but even I'm not that brave.
Exactly.
Well, let's head to Earth. Venus, it's been nice knowing you. We're on our way. The moon! We found the moon. We have arrived home. Well, nearly home. We've got a little pit stop first at the moon. Moon is pea-sized as well.
Moon is pea-sized, yeah, and Earth is more cherry tomato size, maybe a bit smaller, grape size. Earth and Venus are actually very, very similar sizes.
Yeah, are they sister planets? Is that what they get called?
Yeah, you can think of the Earth and Venus as sort of sister planets. Or maybe Venus is Earth's evil twin, right? Because of its horrible climate and its sulfuric acid rain. It's sort of like looking in a dark mirror or something.
So if we turn back now and look towards the sun. Oh, yeah.
Yeah, so if we look towards the sun is the same size as it appears in our sky. And there's actually a really nice trick you can do.
Oh, I love a trick.
So because the entire thing is to scale, if you put your eye level with where the Earth is, you can create an eclipse.
Oh, yeah. I can just see the spikes and it's like a total eclipse.
It perfectly eclipses the disk of the sun, doesn't it?
Yeah, it's an actual spot on match. Yeah. That is fab. So you got your own little eclipse here as well.
Yeah, exactly. Which eclipses won't be around forever as well, because the moon is actually getting further away from the Earth.
Why is that?
Because it's losing energy. So if you think about tidal energy, right, the moon raises and lowers the tides. We can get energy out of that to drive our renewable energy, but that energy has to come from somewhere. And so that energy in the tides, we're basically stealing it from the moon's orbit. And so the moon loses energy and moves away from the Earth. It moves away at around the speed that your fingernails grow, about a couple of centimeters per year. But that means way back in the past, the moon would be much bigger in the sky and would have completely blocked the sun, and you wouldn't get any night eclipses. And, 500 million years in the future, the moon would have moved so far away, it would be smaller than the sun, and you won't get eclipses anymore. So we are living at the right cosmic time to see these eclipses.
Like a very special time to be alive because we get to see the eclipse.
Yeah, exactly. We're very lucky. I find it interesting that Earth is the only planet that was named before we knew it was a planet. Right, so all of the other planets in the sky, I guess we named them before we knew they were planets, but they were named after gods, right? Because the ancient Greeks and the Romans looked in the sky and knew that they were special, and so they named them after their gods. Earth is named after just dirt, right? I sometimes feel we should name it something a bit more poetic than dirt. We should name it Gaia or something. That'd be quite nice.
Oh, that's a good one, Gaia. Yeah, something, like you said, you've got Mercury, you've got Mars, Jupiter.
All these very majestic names, Jupiter, Saturn, then mud.
I've never thought of that. Our planet is literally called mud. So we've got Mars here. This looks like what are they called? Gooseberries? What are the little ones?
Like a red currant?
A red currant. It's Christmas time. That's what I'm thinking of, Christmas.
I'm glad we're ending at Mars. I feel like we're running out of small foods to name these planets.
In terms of science and research, what is something interesting that's going on about Mars at the minute?
There's a Mars rover called Perseverance, which is busy exploring the Jezero crater. It's the remains of a dried up lake on Mars, and is looking for any signs of ancient life. Because in terms of habitable planets, Mars a few billion years ago was pretty spot on.
Matt, I'm going to leave you on Mars, or you might float back to the sun, and I'm gonna keep walking through space.
Amazing. Well, this has been really fun. I've enjoyed walking the solar system with you. It's been great.
It's been brilliant, and now I must traverse the rest alone. Never know who I'll find on my way.
I believe in you.
Thank you. Thank you very much to my space guide extraordinaire, Matt Bothwell from the University of Cambridge.
Welcome to the Naked Gaming Podcast with me, Chris Barrow.
And me, Lee Milner.
Every month we look at the latest gaming news.
The primary way for the farm pigs was really to nose the joystick up and down.
We review the biggest releases.
You can easily sit down, play it, switch off, a bit like Crash Bandicoot, but instead you're inside a horror movie.
And because there's a simulator for almost anything, we play some of the strangest ones available.
I'm kind of like dragging the pigs. The pigs are laying eggs, and then coins are coming out of the eggs.
The Naked Gaming Podcast from The Naked Scientists. Download it now wherever you get your podcasts.
Music in the programme is sponsored by Epidemic Sound, perfect music for audio and video productions.
You're listening to the Naked Scientist podcast with me, James Titko, and Julia Ravey.
I feel a little bit bad about leaving Matt on Mars, you know.
It was interesting to hear Matt say it used to be more like Earth. But nah, I can't imagine it would be a place I would personally want to take a trip to now.
I know someone who does. Simon Morden, planet geologist and author of The Red Planet. He is a Mars fanatic and gave me a rundown of Mars's history, present and past, and he explained how he once held a tiny piece of the planet in his hands and he didn't even know it.
I was working on achondrite meteorites. These are igneous type rocks formed from molten rock, but out in space. I was looking for raw iron and nickel specks inside this meteorite, and I didn't find any. And I thought that was really disappointing. What I did find was I found a lot of iron oxides. So I just wrote a note saying, I think this sample is contaminated, it's been weathered. And it was 6 months later that I discovered that I was half right in that, yes, that meteorite had indeed been weathered, but it hadn't been weathered on Earth. It had been weathered on Mars.
If I were to land on Mars today, what would I be met with? What would I see and how would I feel?
First of all, I definitely advise you to go in a spacesuit because the average pressure on Mars is 6 millibars. That's probably as good as a vacuum you'll get. It'll be cold, Summer temperatures on Mars get up to 20 degrees or so. But on that same day, just before dawn, you'll be looking at minus 80. Because of the cold, all of the water vapor in the atmosphere has basically frozen out. It's still there as ice, basically under your feet, but there will be none in the air at all. It will be barren, and you will have not seen anything like it at all. Not that you can see very far, of course, because the curvature of the planet is such that if you're standing there on the surface of the planet, you will only able to see to the horizon, which is 5 miles away.
If we look back at Earth, it's had great freezes, it's had times when it's been extremely hot. Has Mars had similar changes to its terrain and to its climate over time as well?
Mars, because it formed further away from the sun, ended up with a big load of dust and gas and ice that went into the planet when it was formed, which meant that its atmosphere was ridiculously big to start off with. But a planet that small couldn't hang on to an atmosphere that big. So as that atmosphere was stripped away into space, the surface temperature cooled, the pressure lowered, and it was able to rain. So there was a time when Mars was warm and it was very wet. Literally half of Mars was covered with an ocean. But the loss of its atmosphere was only ever going to end up with Mars getting basically meaner and colder as the years progressed.
And Mars has a pretty big volcano on its surface. So how did volcanic activity affect the planet?
Mars is the site of the highest volcano in the solar system, Olympus Mons, which is 24 kilometers high. That's 15 miles, which is pretty beefy. It's not the only ludicrously massive volcano on Mars. Apart from a small handful that are elsewhere on the planet, they're all centered on this one place called Tharsis. What you've essentially got with Tharsis is you've got this lump of rock that you've stuck onto the side of Mars. And if you imagine that someone has taken a small planet and stuck it to the side of your own planet, it's going to make the planet wobble a bit. And that's exactly what happened with Mars. Tharsis wasn't originally on the equator, but because Mars is rotating once every 24 and a bit hours, the whole of Mars has literally twisted in its orbit so that Tharsis is now exactly on the equator.
And the biggest question about Mars, a la David Bowie, is there or was there life on Mars, do we think?
I am going to say yes. If we look at the Earth's oceans and where we think life originated on Earth, it will be in the deep ocean, where you have things called black smokers. That's where seawater has gone down through cracks in the crust and it's met hot rock. Now, hot water is great at dissolving soluble minerals. Very primitive plants and bacteria can use that chemical soup that comes back out to power their own reactions. If we look at Mars, we have exactly the same conditions. We have a deep ocean, we have cracks in the crust, we have hot rock underneath the crust. If we get down there and trundle around on the northern plains looking for the sites of these black smokers, wherever they might be, we may well find the same kinds of primitive life there that we would have done 4 billion years ago on Earth.
Simon Morden and a condensed history of Mars.
Moving on from Mars then, should we get back to the trail?
Yeah, about that. Yeah, so I didn't walk the rest of the trail. I drove, which is bad, but it's really, really hot today. And so I just thought, I will drive to Pluto. I have my little spaceship here, so I jumped in that with the AC on, and I have reached the last planet. So I'm going to now go and try my very best to find it. And here we are. We've made it to the final planet in Cow Hollow Wood in Water Beach. We're at Pluto. So this is the end of the trail. And as Matt mentioned before, you'd have to walk a pretty long way to find the next star. But now we have an absolutely incredible tool which is allowing us to see beyond our solar system. In fact, to galaxies so far away, they think they are the oldest and furthest we have ever seen. That is, of course, the James Webb Space Telescope. I spoke to Becky Smethurst from the University of Oxford, and she gave me an insight into what we're actually looking at.
It's almost easier to say, what are we not looking at the minute? Because it feels like JWST, or the James Webb Space Telescope, it feels like it's just revealing so much at the minute. But what we're seeing is essentially infrared light from all these objects in space. So this is light that has a longer wavelength than visible light that we can see with our eyes. It's redder. So that means it can see through dust, because this light has a longer wavelength that essentially just kind of goes around all these dust particles rather than getting scattered off it. So we can see into star forming regions, which is really cool. And also, because the universe is expanding and all the light from galaxies of great distances has been redshifted by that expansion, it's been stretched out to these longer wavelengths beyond what we can see. It means that we can actually see some of the most distant galaxies in the entire universe, the most distant, these islands of stars in our universe, which is amazing because if they're most distant, the light that's coming from them has traveled the most distance as well, which means it left those galaxies when the universe was much younger.
There's been all these claims around the James Webb images that we've seen, the oldest stars in our entire universe. But what more needs to be done to confirm how old these stars actually are?
People are starting to pick out what we call candidates for the most distant galaxies, the light from which is the oldest light we could detect. People are claiming, this light left these galaxies 13.6 billion years ago, therefore it's the oldest light. The thing is that we've only found evidence for that in images. Ideally, what you would want to do is take all the light from that galaxy, split it through a prism, to confirm that they actually are at that distance, and also declare which one actually is the furthest away. We're going to need to get the spectrum of light as well, which James Webb have already collected. People are working on it, but there's also cool things you can do with spectra at those wavelengths. Like, for example, you can take the light from an exoplanet, so a planet in orbit around another star in our galaxy, our island of stars, the Milky Way. And you can say, okay, take the little bit of starlight that passed through that planet's atmosphere on its way to us, and we'll see how it differs from the normal starlight that we receive from that star. And any differences essentially tell you what's in the atmosphere of that planet, because say there is water or carbon dioxide or maybe methane or something in that atmosphere, it will steal away a little bit of the light. And so we can actually use this to figure out what exoplanet atmospheres are made of and if they contain water.
That is really exciting. And then if we move away from planets, can you also see black holes in these images?
Amazingly enough, yes. I mean, you can tell I'm excited about this because this is my stuff. And people always get thrown by this, the idea that you can see a black hole, because the idea of a black hole is that it's so dense that light can't escape. But the thing is, the material around a black hole, and especially a supermassive black hole, because of the black hole's extreme gravity, it gets accelerated to huge speeds, which means that it gets hot and it starts to glow, in the same way that, shove a piece of metal in a fire, right? It'll start to glow like in a blacksmith's forge or something. So it starts to glow incredibly brightly, so much that supermassive black holes are some of the brightest objects in the entire universe. They literally light up like Christmas trees. But the thing is, the centers of galaxies where we find these supermassive black holes are really dusty. So we only ever see about half of them. And they're also not that bright in visible light, but they're very bright in infrared light. So one of the images that was actually released of what was called Stephan's Quintet, it was those 5 nearby galaxies that were all grouped together. One of the galaxies at the very, very top, if you look in the longer wavelengths of infrared light in the image that was released, there's just this giant, bright, blazing thing in the center of it. And that is the gas that's swirling around the supermassive black hole. And it's amazing that we're going to be able to pick them out at that distance as well.
Now that we have these images and we're going to be able to analyse them, and we've seen the power of this telescope, how do you think this will change our thoughts on the universe?
I don't think there's going to be an area of astronomy that isn't touched by what JWST is going to find. And that's the thing, is that we've designed it to do various different things, to see these exoplanet atmospheres, to peer through dust where stars are forming, and to see back to the oldest light in the universe. Not only are we going to get all these observations that we plan to take, but all these observations we didn't plan to take. And who knows what we're going to find. And that, I think, is what I'm most excited for, what you call these sort of unknown unknowns, the things that we didn't even know to ask as we were designing this telescope. I think in 20 years' time, we're going to be like, wow, that thing that we never knew when JWST launched that now has changed everything. We can't call what it's going to be, but I think it's going to be big, whatever it is.
Becky Smethurst from the University of Oxford and author of A Brief History of Black Holes and Why Nearly Everything You Know About Them is Wrong, summarising some of the amazing things the James Webb Space Telescope has shown us so far.
I suppose I'll have to let you off not walking the 9 kilometres in 34-degree heat. The scale of that project and jumping out of our solar system from the work Stephen is doing and what the James Webb Telescope is revealing really does create a sense of how small we are. Not in a bad way, just like, wow.
Yeah, and I love that was the main message of the Our Place in Space project. That was what it was trying to project, that we are all on this tiny rock together. There should be no us and them, but a united Earth. Looking at ourselves as part of this massive universe is good for some perspective.
Indeed it is, and that's all we have time for this week. Come back next time where we'll be taking a look at water distribution. With droughts declared across large areas of England over the summer months, how can we move water to the places that need it most? The Naked Scientist comes to you from the University of Cambridge's Institute of Continuing Education. It's supported by Rolls-Royce. I'm James Titko, thanks for listening, and until next time, goodbye.